Good evening, I'm Gina Sapiro. I'm the Dean of the College of Arts and Sciences, and welcome to the first annual Silas Peirce Lecture. The Silas Peirce Lecture is a renewed signature event of the College of Arts and Sciences. It invites the entire Boston University community, students, faculty, staff, alumni, and other friends to join together for a presentation reflecting the best neighborhoods of the new frontiers of knowledge in any field of inquiry represented by the college. That offers a very wide scope indeed for consideration, as CAS's departments and programs represent a vast number of fields across the humanities and the social and natural sciences. Each year we will offer a lecture representing a different field of study. What better way to launch a series to take us to the new frontiers of knowledge than to begin by visiting Mars? This lecture's namesake, Silas Peirce, was a prominent citizen of Boston. Born in 1860, he was graduated from English High School in 1878. After a visit to Europe, he entered his father's business, the wholesale grocer Silas Peirce and Company, established by his great-uncle, and eventually became its president. Peirce was associated with many businesses and charitable organizations in this region. His winter home was in Brookline and his summer home in Scituate, on land that had been occupied by his family since 1642. Peirce was a treasurer of Boston University and a university trustee, positions he held until he died in 1922. To honor him, his heirs established the Silas Peirce Fund with the intention of providing for special lectures at the College of Liberal Arts, as it was then known. We are grateful to them and, of course, to all of the alumni and friends of Boston University whose generosity allows us to bring wonderful opportunities to the Boston University community. Tonight's speaker will be introduced by Professor Paul Withers, who joined the Department of Astronomy as an assistant professor in 2010. Paul received his BA and MA in physics from Cambridge University and his PhD in planetary sciences from the University of Arizona. Paul's been involved in an amazing range of projects, including about 10 different planetary exploration missions. These include 3 Mars orbiters, MAVEN, Mars Express, Mars Odyssey, 5 Mars landers, Curiosity, Phoenix, Spirit, Opportunity, ExoMars, 1 Venus orbiter, Venus Express, and 1 Titan lander, Huygens. Not surprisingly, he was a recipient of a prestigious NASA Early Career Fellowship. And that's just the description of the guy who's going to introduce the speaker, Paul Withers.
Good evening, everyone, and thank you very much for coming out to see the lecture this evening. It's my pleasure tonight to introduce today's speaker, Dr. Bethany Ehlmann. Bethany did her undergraduate work at Washington University in St. Louis, where she first caught the Mars bug working with 2 earlier Mars rovers, Spirit and Opportunity. She then crossed the Atlantic to study at Oxford as a Rhodes Scholar before returning to the US to do a PhD at Brown University, this time working with data from a spacecraft in orbit around Mars. She then crossed the Atlantic again to work in Paris as a Marie Curie Fellow, returning to the US a few years ago to a faculty position at the California Institute of Technology, where she is today. And that was where she started working with the Curiosity rover. And tonight she will talk to us about following the water on Mars, roving with Curiosity. Please join me in welcoming Bethany Ehlmann.
Okay, so thank you all. It's a pleasure to be here this evening and speaking on this topic. So thank you for the invitation. This is indeed a truly interdisciplinary task, and so I think hearing the background of Silas Peirce, it's appropriate actually to start with a planetary science mission, which involves the work of engineers, geologists, atmospheric scientists. and accountants and secretaries to keep it all on track, to keep the project moving. So I am one of over 400 scientists that's a part of this team. So, and I'm going to present sort of the collective work of the scientists and engineers over the year of Curiosity, over the year of roving Mars with Curiosity, and also explain a little bit about why we're doing this and what we're discovering. So how I got into planetary science basically has a lot to do with this picture. So you may recognize the image. It is not Mars. It is looking at our own Earth from the moon, taken from the Apollo 8 astronauts in orbit. And I think what this highlights, right, is juxtaposition of the lifeless moon juxtaposed with this rich, beautiful swirling orb of blue and white clouds. And we know that this small planet is teeming with life. It's a place in the solar system where throughout the last 4 billion years of its history, it's had life of one form or another. So the question is, was Mars, or other places in our solar system for that matter, ever like this? So Mars today looks like the image on your right here. It's dry, it's dusty. The red color is from iron oxide dust. There's ice in the polar caps. But did Mars once look a lot more like our own Earth, a lot more like the image on the left? So just to get everyone on the same page, I'm a planetary scientist, switch planet, one planet to another, no problem. But just to get everyone on the same page, so Mars is smaller than Earth. It's about half the radius. In terms of, it takes twice as long to get around the sun. In terms of the length of the day, it's more or less the same, a little bit longer. In terms of the tilt on the axis, it's about the same. So Mars also has 4 seasons. The really key parameters are these guys right here in terms of being key to the differences. So Mars receives only 43% of the flux from our sun. It's further away, right? And it has a very thin atmosphere. So it's 95% CO2, but it is 0.6% the pressure of our Earth's atmosphere. And those two things together lead to this average surface temperature of minus 63 degrees Celsius, so considerably colder than our own planet. But in terms of the rocks that it's made of, it's largely similar to large portions of our own planet. So water on Mars. So around, this is a topographic image of Mars, and it's tilted so that we are looking at the northern part of the planet. This is the southern part of the planet, and you can see channels draining down from these high stands in the south to these lowlands in the north. And for all the world, it looks like this basin should have had an enormous ocean, right? So this was the state of the science in the 90s. Looked like it once had water, huge channels flowing out, but there was a problem that the mineralogy, the chemistry, there was no evidence that the water interacted with the rocks, creating the kind of chemical and mineralogical fingerprints like carbonates and sulfate salts, clay minerals from weathering, all those things we classically associated on Earth with water sticking around for a long period of time. So how long of a period of time? What are we talking about when we're talking about exploring Mars and water on Mars? Well, let's actually start a little bit to contextualize why we're exploring and when in history we're accessing the rock record. Here's some context. We'll start with Earth. So here's a schematic, the timelines of 2 planets, our geologic time scale, Mars's geologic time scale. The oldest rocks on Earth are over 4 billion years old, dating from the Hadean period. The oldest rocks that are related to water are somewhat later, around 3.8. The oldest fossil life dates from around 3.5. But important things like our atmosphere getting oxygen, that didn't happen until about 2 billion years ago. And that was largely driven by the rise of microbial oxygen-producing microbes. Now, so a number of critical events in our own history and understanding the process of, okay, what geologic processes combine to create worlds that can sustain life. A number of these processes, right, they're all from the first billion years of history. But a reality is that because of plate tectonics on our planet, less than 1% of our crust is left from this period. And what remains has been deformed into mountain ranges and is somewhat a degraded record. Now, as a planetary scientist, though, if I want to know what's going on during this period, how things like impact cratering or early atmospheric processes are affecting bodies, it's fortunate that we have other planets to look to for this information to find out what makes planets work. And so that's Mars. Other studies that I won't talk about show that the valley networks that I was showing on the earlier slide, they're active during this critical time period on Earth where we're seeing the oldest fossil life and also somewhat later in Mars history, but largely stopping. Likewise, the record from orbital data has shown that we have evidence for hydrothermal system, lake basins, acid groundwaters. Mars has been, all of the mineralogic and chemical fingerprints of water have now come to bear in sort of the last 5 to 10 years or so, which is why you may have seen the headline, "Water on Mars," over and over again. It's one of the most overused headlines of the decade, I think, of NASA exploration. But what it means is that we're discovering all of these different types of water-rich environments across the planet. But we still don't really understand why. Like, why did most of these exist early in history, and then what caused them to shut off? So that is one of the goals of the Curiosity mission. And we also want to understand, did those environments ever support life, and could they have? So Curiosity's mission, formally, is to explore and quantitatively assess a local region on the Mars surface as a potential habitat. So could this region have supported life? And in fact, also, are there chemical clues of life in the rock record? So there are 4 aspects to the mission, actually. One is this search for biological potential. A second is understanding geology and geochemistry. A third is overall understanding the role of water in its cycling. And then the fourth is actually driven by concerns for us, humans, today. And that is, what is the surface radiation environment? If we are, for example, planning on exploring Mars, we need to know the types of hazards that astronauts would face. So it's a combination of fundamental basic science about what is it that makes planets that can support life, how did they change through time, and then can these planets support humans today? So, well, we only have one rover. We have to decide on a landing site for the rover. And this was a long process within the community. This is something I managed to get involved with as a graduate student, because I was looking at orbital data, peering down on the surface, wondering where is it that we can land. Well, what was eventually settled upon after about 3 years of meetings and discussions was that we would visit Gale Crater. It's in this very interesting region of Mars. So this is, again, a map that's showing topography. It's showing elevation. And it's at a very interesting part of Mars, because Mars has this boundary between the southern highlands and that northern lowlands that I showed earlier that could have potentially held an ocean. So, and you can see, actually, those of you who are in the front can probably see exceptionally well that there are channels, river channels, that head down into Gale Crater and then perhaps out continuing into the lowlands. Also, Gale Crater is on this boundary, and it's relatively low. In this case, in this color scale, these low features are 5 kilometers below zero, or the equivalent of sea level on Mars. So it's the deepest hole in the planet in many ways. So if you're going to look for past water, you might as well look for the deepest hole, the deepest basin in the crater, as a place that's likely to hold sediments. The final interesting feature is this central feature. You notice it's considerably higher in the middle of the crater. And that's because the middle of the crater holds a feature, Aeolus Mons, which we've nicknamed Mount Sharp, after Bob Sharp, a geology professor at Caltech, who first described sedimentary features on Mars. So Mount Sharp here is 5.5 kilometers tall out of the center of Gale Crater. And you can see this places it in pretty good company among some of Earth's tallest mountains. What's special about Mount Sharp, you can see it here, is that it's not this homogeneous mound of rock. It actually has layers in it. It's been eroded by channels, and you can see, coming out here on the sides, layers. Now, we have no perfect idea of how this formed. In fact, that's a huge question among the science team. Was most of this mound formed as lake sediments piled up, one right after the other in the crater, filling it, and then eroding it all away? Or was the process actually more complex and slightly less intuitive, where maybe it filled part of the way, but then maybe there was some feedback between winds depositing material on top, sweeping around the crater to the bottom? We don't know exactly, but we have the potential here to find out. One of the things that was intriguing, we're going to now zoom in here, is that we're able to look with the orbital data at composition. What is this made of? Well, the answer is that you can see in the color, this is a false color image, you can see these successive layers of color as we head up to the top. And using orbital data and a combination of spectroscopy, we can actually nail down a stratigraphy that goes through different layers of minerals with clay minerals, iron oxides, hematite, sulfates, other features in a kind of stratigraphy that looks like this. So those of you who have gone hiking in the American Southwest or gone to the bottom of the Grand Canyon know that it's these stratigraphies that geologists get all excited about, right? It's a stratigraphy that has the organized rock record that preserves what the environmental conditions were through time. So we geologists were all super excited when we saw the stratigraphy of Gale Crater, because what this preserves is a time record from some of Mars's earliest history, one different type of mineralogic environment after the other. And just to zoom in here, you can see closer up some of the different layers and how they're eroding. So this is what we wanted to send a rover. I mean, we can't yet send people there ourselves to go hiking up as we would the Grand Canyon. This is where we wanted to send the rover and trace through this history, reading it from bottom, oldest, to top. What were the environmental changes? Okay, so let's introduce the rover that's going here. What's on Curiosity? So Curiosity is certainly the most capable mobile laboratory ever sent to another planet. So the acronym MSL, Mars Science Laboratory, refers to the rover and the 10 science instruments that it carries. From an environmental package to sense water and hydrogen in the subsurface, a weather station, a camera for imaging, the sensor for measuring radiation, on the arm, instruments for driving up to a rock or a soil, deploying it, looking at the chemistry, looking at microscopic images. It has a drill, a scoop, a brush, and a set of sieves for kind of processing samples. And it also has 3 instruments and 3 capabilities that are actually entirely new for planetary exploration. A set of instruments here that measures isotopes, not only of the atmosphere, but of rocks and soils, an X-ray diffraction instrument for mineralogy, and then ChemCam, which is, I think, my favorite and often an audience favorite, because ChemCam shoots lasers at rocks and soils and looks at the plasma for elements. So yes, we drive around shooting lasers and soils with rocks from our rover. It's actually quite fun. So Curiosity is not the first rover. It's part of an evolutionary history of rovers, and here's the family portrait. So some of you may remember in July 4th, 1997, the first rover, airbag bounced, landed on Mars, the little Sojourner rover, followed by Spirit and Opportunity, and now Curiosity. And so it stands 2.8 meters high. It is quite tall. And to give you a sense of scale, this is some of the members of our science team during an operations test in our test bed. We got to practice 6 months before landing what we would do once it arrived on the surface and drive around in the laboratory test bed and measure rocks. So this is taking a look at the rover, and you can see how it compares to the size of a person. This is how the back shell that it's packed in compares to a Mini Cooper. So it's the size of about this, a little bit bigger than a Mini, actually. And this is the rover itself being packaged in that same back shell at the Cape, getting readied for launch. And you can see its wheels are kind of tucked up in sort of a rover origami to pack it into the back shell. Then the entire last stage is loaded onto the top of an Atlas V rocket, and this was back in November of 2011, and then launched just after Thanksgiving from Cape Canaveral. Now the journey to Mars, so launch is the first hard thing. It's always a little tricky. Launch is the first hard thing. The second hard thing is hitting Mars. So the way this works is that given the orbital mechanics of the situation, Earth at the 3rd slot out from the sun, whipping around, and Mars at the 4th, the way it works is that every 2 years or so there's a close point where if you launch within a particular window, you can arrive on Mars within about 7 months. So you launch when Earth is trailing Mars, launch, and then gradually the trajectory takes it so that the spacecraft catches up to Mars. So 7 months is the quickest that you can get to Mars. even though while the rover was just hanging out, tucked in its back shell, it was still doing science. And that's because the instrument, RAD, aptly named to measure radiation, was counting away. And so we wanted to count what is the environment that a human would experience taking this same journey in place of the rover. What you see here are the data. So this background is in radiation is mainly due to the influence of galactic cosmic rays. And these spikes that you see, though, are the dangerous part. This is the activity due to our sun and the radiation that it would be, well, that affected the RAD detector and that would affect any humans along the way. Convolving these data into dosages, which is sort of how any health situation, so dose equivalent, millisieverts is the units. Just comparing here, on this case, it was 6 months of the transit to Mars, how that compares to, for example, spending 6 months on the International Space Station. You might say, oh, it's similar, but actually this is a logarithmic scale. So 100 here for the International Space Station, and about 3 times as much then to go to Mars. So considerably exceeds that a radiation worker limit would receive. So what this says is that it's not impossible to get to Mars, but this says we certainly have to bring some shielding along the way. But this helps us quantify exactly how much. Now the fun part. Okay, so launch is hard. Trajectory is pretty hard. Some spacecraft missions have failed because they've missed Mars. The really hard part, though, is how do you land a Mini Cooper-sized object softly on the surface of another planet? So what I'm about to show is the landing site video of the sequence of events as the rover enters the atmosphere of Mars. From top of the atmosphere going at 13,000 miles per hour to 0 on the surface. It takes 7 minutes. And this is the sequence of events. This is the events the night in August when it landed. And you're going to see some photos occasionally. Some of it's computer simulation, but you're going to also see some pictures and images off to the side. And those are ones that are actually snapped by the rover by a descent camera in the belly as it's going down. So I'll just let you watch.
Things are looking good. Vehicle reports entry interface. At this time, we'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry. We are beginning to feel the atmosphere as we go in here.
So it's firing thrusters to stabilize it.
Vehicle just
Hits the
reported
top
via
of the
tones that
atmosphere.
it has started guided entry. At this time, the vehicle is beginning to steer its way to the target. We have seen peak deceleration. That is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Earth G's. Bank reversal 2 is starting. We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Heat shield has separated. We're found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending. Standing by for batch shell separation. We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is starting.
Eagle eyes, you remain strong.
Touchdown confirmed. We're safe on Mars.
Yeah, I mean, as you can imagine, this was a moment of huge celebration because that landing system's pretty crazy, right? many steps, and all of them have to work perfectly for this to be successful.
Thumbnail.
And that was it. So 7 minutes, and then the first image coming down here from the rover showing beautifully, perfect landing, shadow in front of us, and then our target, Mount Sharp, in the foreground. So as you can imagine, we were all incredibly excited. And those of us on the science team, right? So this was the engineering team's work. I had nothing to do with the landing. We were all sitting there nervously wondering if we were going to be getting to work in the next hour or if we were going to be going home. So obviously we stayed at work. It was incredibly exciting. I'm over in the back here giving some of my colleagues a high 10. I couldn't sit during landing. I was pacing around. I don't know about all those people who were sitting down. So here is where we landed at the particular patch of ground. So Curiosity landed here where you see this dark spot, and you can see the detritus of that landing system, right? The parachute as it was released, the back shell as it dropped off of the rover. The heat shield ended up far away. That was the first to go. Then the parachute out, the back shell down, and then the sky crane, which delivered Curiosity to the surface at the last minute, had a divert maneuver to go away and crash so as not to end operations on top of the rover. So here it all is, all the pieces, and it all worked incredibly well. So we set about exploring this new site, and the dark is because the thrusters at the end blew away the bright Mars dust over the surface. So this is our landing site, and you can see these scour marks, in fact, from where the sky crane and the rocket engines were firing and blowing away the portions of the surface. So we sat down to explore, and there are many aspects of exploration. One of the first was actually exploring atmospheric and environmental conditions. So what is it like on Mars? Well, our weather station, the REMS instrument, says this is the temperature profile for time on Mars. So this is a sol. A sol is a Martian day, a solar cycle, a Martian day. And I've put it in Fahrenheit here in the peaks, and you can see so sometimes it gets colder or warmer on Mars than it does in Massachusetts in the winter. Peak daytime temperatures of 37°F. I mean, sometimes that's a balmy day in the winter here, right? Now, on the other hand, the nighttime lows are a little less favorable. So one of the reasons for this huge temperature flux over nearly 100 degrees Fahrenheit between day and night is because the Mars atmosphere is so thin, and so it doesn't retain heat, and so it gets above freezing in some cases, but then deeply below freezing at night. So the other instrument to make atmospheric measurements is this sophisticated laboratory, SAM, the Sample Analysis at Mars, the gas chromatograph mass spectrometer on the rover. And this is the most complicated instrument sent to another planet, I think, fairly easily. It weighs 70 kilograms. And you can see all the valving and wiring required to do all of these functions. Well, and what it does is it sits in the belly of the rover, and samples are ingested here, and they go inside into some sample cups. One of the things it's able to do is measure very precisely the composition of the atmosphere. What gases are in the atmosphere? We can do this telescopically from Earth to some extent. We also did it with the Viking landers back in the 70s, but these are the most refined measurements of the composition of Mars's atmosphere. So nearly 96% CO2 with argon and nitrogen occupying the other positions. You can see not a lot of oxygen around at the surface. The other thing, and so a few of you in the audience may be aware of this and this question. So a while ago, I think about 4 years ago now, actually a little longer, 5 years ago now, it was reported that there was methane, a particular gas, CH4, in the Mars atmosphere, and it had this sort of characteristic distribution at a parts per billion level. But this was nonetheless significant because methane is not thermodynamically stable in the Mars atmosphere. It actually dissociates, it is destroyed very quickly. So the fact that it existed was pretty cool because that it existed at these quantities was pretty cool because it meant one of these things. Cometary influx was insufficient to explain the quantity. So it meant that either Mars's volcanoes were belching out methane, that there were hydrothermal systems beneath the surface in chemical reactions with water and rock creating this gas methane, or that there was microbial life. Microbes produce methane and commonly on Earth, so were these on Mars the source of the methane? Interestingly, we have not yet found it on the Curiosity rover, although we've only been here we've been here a full Earth year, but that's only half of a Martian year. So if this is seasonal, there might be something yet to come. So this is a puzzle. So just keep an ear to the news about methane on Mars. The other thing, those of you who are in the audience who might be aficionados of isotopes that this laboratory does is now for the first time we're getting isotopic compositions of rocks and minerals from the surface of Mars. So this is a sample of sand, and we're able to pin down the isotopic composition and compare it to meteorites and other materials from Mars, as well as the atmosphere. And this is important because it allows us to then start to create quantitative cycles of how carbon, how water, how all these things cycle through the Mars system. And this is the basis for how we know how things geochemically cycle on Earth. The other thing in terms of environmental conditions is that the RAD instrument was still hard at work. It actually turned out to be a relatively quiet year on Mars so far, with one exception, only one solar particle event. So our dose equivalent here was the transit to Mars. Okay, just 180 days on Mars gives you the same radiation dosage as the transit to Mars. And that's because Mars does not have an ozone layer to protect it. It does not have a appreciable magnetic field. And so on the surface of Mars, a human would be more exposed to the radiation environment. So it's something we have to plan for if we plan on going there. Okay, so that's the environment story. What about the water story that brought us there? Those minerals, those channels, the heading into Gale. So the water story, actually, we were quite fortunate. The water story started from our landing site in some of the materials that had been disrupted by the action of the thrusters. So this is one of the patches that had been scoured away, and you can see these kind of mottled-looking rocks. One of the things we were able to do before we could even drive, before the wheels and the mobility were checked out, is we could shoot at them with our ChemCam instrument. So we got a good idea of the composition, what these were made out of. And so you can see here, we're making a little indentation, a hole from about a few meters away on the rock. And this is what it looks like on a sand here. We shoot the laser, the material ablates, and then we see emission lines from the plasma that indicate composition. But then we were able to drive closer. And you can see the blocky, sort of cemented together appearance continues. And in fact, when we zoom in, this on the left is what we see. So these are, you notice that this is not a kind of homogeneous rock. There are clasts in here, small pebbles. And you can see that these pebbles are not angular, they're rounded. And that's important because if you just break a rock, like you you would break it with a hammer here on Earth. On Mars, you might break it with an incoming meteorite. But if you just break the rock, it creates all kinds of angular fragments. What you need is them tumbling around in, for example, a stream to round off the edges. And what we see here are rounded rocks, very similar to what we find in high-energy stream channels on Earth. So this was our first sign of water on Mars, and minus the trees, minus the blue sky, the environment at one point probably looked something like this, fairly vigorous flow down a steep slope to round these few centimeter size cobbles. But they're only partially rounded. They're not like perfectly smooth pebbles like you would perhaps find along some ocean shores or in some certain streams. So having made our first big discovery about water on Mars, my goodness, high energy flowing water, it was now time to rove. So relative to our particular landing site, we couldn't land right on Mount Sharp. It's difficult enough to land a 1-ton rover on Mars with a sky crane. It's too hard to land it on a mountain. So we had to land off to the side and then drive to the mountain, which was this direction. So where do you think the geologists wanted to go? So those of you who might have geological eyes would look at this image and say, my goodness, there's one rock unit that is dark and fairly smooth. There's another that's dark, but maybe it's more competent because it's holding on to these craters quite well. And then here's this other light-toned rock unit. So where did the geologists go? Toward Mount Sharp? No. We went here. Discoveries are sometimes fortuitous. So we drove on the way because the thought was that these layers, and if I were to zoom in further, they're very fine-grained, and this is one of the lowest points in the crater. So the thought was, is if there were ever lake sediments, well, maybe they were here. And what is it anyway, this contact between all of these rock units? So we were going to drive by, check it out. So that's what we did. That's where we started heading. And we were going to use our analytical laboratory, our SAM instruments, on rock samples here for the first time. So set out driving. And this is a color image from the HiRISE orbiter. And you can see the rover making its tracks, disrupting the red dust on the surface as we headed off into the distance. So the first thing, though, wasn't strictly that we had to do, wasn't strictly science. We were still in checkout mode, and one of the objectives of the rover is to seek potential signs of biological activity, potential life. But it's a problem because on Earth there is basically life everywhere. I mean, microbes, anywhere that there is water, there is life, and microbes cover basically every surface of this planet. So it's very hard to get a spacecraft clean. Also, rockets employ fuels like hydrazine, which is chock full of organic material. So while it's traveling in space, while thrusters are firing, we could get some further contamination in our instruments, even if they were perfectly clean when they left Earth. So the first thing that we were looking for was a good sand dune, because what we were going to do is, so the rover has a scoop to bring in material into the analytical instruments. The first thing we wanted to do was clean the scoop. So the first thing we wanted to do is go to Mars and do a particular housekeeping task, which is fine, cleanliness is good. So we headed over to this very small, I'll just go back for a second, to this very small sand ripple. It was actually kind of hard to find sand at this particular, but we wanted to find it soon so we could analyze those cool light-toned sediments. So we found this little sand guy, scuffed it with the wheel just to make sure that it was sand. I mean, we thought so, but you never know. And then did scoops. 1, 2, 3, 4, 5. So scoop 1, scoop, shake it through the sampling system. Don't put it in analytical instruments, dump it out. Shake, dump. Scoop, shake, dump. Scoop, shake, dump. And on number 5, we took the sand and we exercised the chemical and mineralogical instruments on the Mars materials for the first time. And it was actually kind of exactly what we expected to find, and kind of weird. So what we expected to find was normal Mars basaltic sand. This has been measured at many landing sites before. It's similar to if you were to take a rock from any basalt anywhere on Earth, northwestern US, Hawaii, Iceland, Deccan Traps in India, grind it up into sand. It looks something like the mineralogy that was measured with the ChemMin instrument. What was puzzling, though, is that there was over 25% didn't show up with any kind of a mineralogic signature on the instrument. It's amorphous, which means that at a sort of 2-micron scale or less, that's the limit to the atomic structure. So it's really grungy, rusty stuff. And that was a little bit of a surprise. We did not expect that. Furthermore, when we put this sieved sand into our instrument SAM and heated it up, and looked at the release of gases as a function of sample temperature, there was actually a large water peak, far more than we had expected. And this sample of sand had 3 to 5 weight % water in the sample. So the dust of Mars is mostly ground up basalt, but there's some portion in there that actually carries water. And this is important, not only for understanding, well, where's the water on Mars, but also for potential resources. If we as humans go, well, maybe we can get some water to drink and to do all sorts of things by processing some of the soils. So this is cool. But we weren't here to measure sand, we were here to measure rocks and do stratigraphy. So we drove to those light toned layers, and this is what we found. This clear contact between an overlying, more competent unit and these softer materials beneath. And the reason it was interesting became apparent once we got the color photos down, right? So now you can see this lip, it's about 10 centimeters high, so about that high. But it's what's underneath that's cool. So you see these nodules, these gray nodules, and then you can see these white veins cutting through the sedimentary layer. So if we take a close look at these veins, you can see them here. This is something we typically find on Earth in environments where there's a shallow lake, like again, desert Southwest, deserts of Australia, Sahara. There's a shallow body of water that's evaporating, and as water is wicking up through the ground, it's depositing minerals as it goes, as it evaporates. And so this is what we're seeing on Mars, and a probably equivalent environment on Earth. And these are the chemical data from ChemCam. So shooting our laser shots at these veins, when we're on a vein, which are the colored materials here, the colored lines, you see it's enriched in calcium, it's enriched in sulfur when we're in the vein, and it's enriched in hydrogen. So this is a hydrated calcium sulfate material like gypsum that we found here in the veins of this rock on Mars. But we can do more than shoot with ChemCam. So we can scoop things, and we can also drill. So that is what we did. The rover has a drill that makes sort of dime-sized holes and then ingests the powder back into the sample handling system. So the before and after, and you can see we're exposing definitely materials of different composition. Looking down that dime-sized drill hole with the microscopic image, you can see again these veins of gypsum. And these are the little holes where the ChemCam instrument shot. That required a lot of work to shoot down a dime-sized hole. It wasn't designed for that. That was us like ad-libbing on the fly. Okay, so we took the powder, we would take two drill holes. What you do is the drill bit sucks it in, and then it goes through the sample handling system. You can even open it up again because it falls in the scoop. You can open it up, take another look at it, and then you can pour from the scoop into various inlets. And so I already have featured SAM, the incredibly complex gas chromatograph mass spectrometer. The other laboratory instrument that sits in the belly of the rover, this is the intake valve for a small sample holder for the ChemMin instrument, which shoots X-rays out of a tube through the sample, which is being vibrated by piezoelectronics. It's like a tuning fork, going back and forth here, vibrating the sample, and then the X-rays are diffracted in characteristic ways depending on the mineral structure. And what was neat is that this is what the pattern that we saw with the sand shadow, and this is what we saw with the drill powder. A different pattern, particularly here at lower, shorter, smaller size range of orders that indicate clay minerals. And clay minerals are neat. They're a product of weathering. They mean water was there through the samples for a long time. So we found clay minerals in these sedimentary rocks with these veins of salts running through them. So what's the idea? Here's what we think this part of Gale Crater experienced. So you can see there's a breach in the rim where a channel feeds down. This channel heads down toward our landing site. We landed about right here is where we came to rest. So water's flowed rapidly down the crater wall, creating those conglomerates, tumbling the rocks around, and then ponded in a shallow area where the clay minerals, the sulfates formed, and then evaporated. So there was a shallow lake here, and the clay minerals and the sulfates together indicate an environment that was actually pretty benign for life. In contrast to some of the other findings of the rover that found acid environments, this was a neutral to alkaline pH. If you went out on Earth, this lake would be teeming with microbes and maybe even fish. No fish on Mars, probably. So this is a dry lake from Australia and a sediment core from it, and this is kind of what we think is the best analog, are these shallow playa lakes in desert type environments. Okay, finally, the other cool thing that we've done, and you may not think this is cool, but for planetary science, this is really neat. The other thing we were able to do is, for the very first time, we were able to make an age measurement on the surface of another planet. And this is incredibly hard. Planetary science, for the most time, has been bedeviled by this problem of, okay, well, we can tell if something is over something else, like what their ages are. But in contrast to Earth, where you just take your sample to the laboratory and you do some radiometric dating and have an age, it's a very straightforward process of radioactive decay. You can't do this on Mars until now. With the capabilities of the SAM instrument, you can look for the isotopes of these and make estimates of the rock age. So we did this for the first time with the scooped material for the mudstone, and it sort of makes sense. The age that came out of it was an age that was quite old, 4.2 billion years ago, but what this age is it's the crystallization age of the rocks in the rim that were eroded down and deposited in this lake. So it's the age that the crystals of the like in this case feldspar minerals formed. And this matches very well with the estimate from superposition of craters as to what the age of Gale is. The other thing we were able to do is get an age of how long the particular material had been exposed on the surface of Mars by measuring the cosmogenic isotopes that are built up through time, and then being able to get a rate of retreat of the scarp based on the quantities of the amount of buildup of these cosmogenic isotopes. So this is really cool. It's the first time anything like this has been done on the surface of another planet, and we're gonna look to do this elsewhere on Gale and kind of build the story of filling and erosion and when the formation events happened. So the future, what's next for the rovers? And I'll end it here, but then take some questions. So the future. Well, right, so we were supposed to go here, and we spent about 9 months of the first year going there. But look what we found. We found evidence of a past lake that for all the world was a perfectly habitable environment. But then it was time to move. That's not why we came here. We came here to climb our way through that stratigraphy in Mount Sharp. And this is that stratigraphy. So this is an image snapped by the rover on the surface. It's a false color image, so it enhances the compositional differences. And this is the environment that we're going to explore. And you can see the layers up through the mountain. So for scale, those of you in the front can maybe see there's a tiny boulder there. And that's the scale of the Curiosity rover. So this is a bit of a mountaineering job. So we started here, we went here, and now we're on the trek down to this entry point. We want to avoid climbing through this huge sand field here, so we're heading south to cut through the dunes and then start climbing up these various rock layers. So we're nearly halfway there. It's been a little bit over a year and a half, and more of the trek to go. So we've trekked about, let's see, a little over 5 kilometers at last count. So these are the rover wheels. Notice this. So that is meant to be there as tread. That is not. It's bad when you can see Mars on the other side of your wheels. There you can see Mars. And you can see that the wheels are taking a beating. And this was a bit unexpected. It's because this landing site is at a small scale, not at a big scale, but at a small scale, is considerably rockier than ones we've seen before. And perhaps because of the winds, the rocks are somewhat pointier. They're pyramidal shaped. So rather than just being kind of random rocks strewn on the surface, they're rocks strewn on the surface but then eroded by wind so that they actually have a point to them. And the rover is running over this. So this is problematic. The wheels themselves have an alloy frame, so even if the aluminum covering wears off, it'll still be able to rove. But the problem is we want to climb up slopes. So the more surface area that we have when we're climbing up the slopes of the mountain, the better. So we want to keep our wheels intact if at all possible, which means we all, again, set off on a search for sand, because if the sand's there, it's covering up the pointy rocks. So pointy rocks, sand. So which way did we go? Sand. But the question was, can we go over this? It's like this high. We don't want to get stuck. That would be embarrassing. Not to mention a waste of a perfectly good $2.5 billion mission. So, though, this had been anticipated. We knew we were going to face dunes at Gale Crater, so the system had been extensively tested in the field out a couple of hours away from JPL on some of the large dune systems. So the first thing was, again, to check, it looks like sand, but is it sand? So we scuff it with the rover wheel. Then we take a close look with the microscopic imager. You can see it's sand, but there are some subtleties, right? It's sand that's armored by these coarser grains, with much finer materials beneath. So these are kind of clay dunes, but we were pretty sure that this would work. So we went partway up, sort of seemed to still work, and then climbed over the dune. You can see the tracks heading out the other side. Now we're on the sort of sandy path to Mount Sharp, so we can drive faster actually, because we're not worried about avoiding these pointy rocks. So we continue trekking, we continue tracing out the history of water. Gale Crater is somewhere here on the plot. So we're really in this critical period of Mars history where all kinds of different environments exist, trying to understand them. But this is a story that I could give in another talk, but this is an example of everywhere that we've seen a mineral related to water on the surface of Mars. And most of this has all been discovered in the last 5 years. Gale Crater is just one of these points. So there's an incredibly rich record of the early history of our neighboring planet in the first billion years of the history of the solar system, of the history of this planet, available for exploration. We just have to go to a few more of these points. And I'll end with a bit of astronomy, because in addition to environment, geology, looking for signs of life, which we haven't found yet, the rover does astronomy occasionally. So here's a night sky. You cannot even discern the dot in this projector, but if we look here, actually you can kind of discern the dots, and then zoom in, there are 2 dots. What this is the Earth and the Moon, as seen from Mars. So I think that puts a little perspective on it. Our neighboring planet, in some ways similar to us, but yet fairly far away. So with that, happy to take any questions. Thanks.
Thank you very much, Bethany, for a lovely presentation. Now, if there are any questions from the audience, we have a couple of microphones in the aisles there, if anyone would like to make their way over there. And I shall use my prerogative to ask the first question. I'm interested in what it was like when you were first driving the rover around on Mars and you were operating on Mars time, this 24-hour, 40-minute days.
Right. Okay. So many of you may not know, so I mentioned briefly, so the Mars is, we don't joystick the rover. There's no one sitting at JPL going, and it's moving in response, although that would be totally fun. Instead, it takes light, because of the distance, it takes light between 10 and 25 minutes to reach Mars, depending on where Earth and Mars are in their orbits, which means it takes any signal that you send. So when we plan one Mars day at a time. Now, because the Mars day, as you pointed out, is 40 minutes longer than the Earth day, and if you're planning on Mars time, if you want to be most efficient, which we did at the beginning of the mission, you go into work one day at 8 a.m., one day at 8:40, one day at 9:20, one day at 10. It's all very pleasant. You're moving forward later each day until you're coming into work at 2 a.m. and 2:40 and 3:20, and then it gets somewhat tedious as we march through the cycle. So Mars time is kind of bizarre in that you start, in certain periods, you live completely out of phase with the people in the world around you. It's like shift work, but it's this strange migrating shift work where no one knows how out of phase you're going to be.
Thank you. Now, is there anyone who'd like to come up to the microphones and ask a question? The nicely dressed gentleman over there.
So I had a question about the Muma et al. Result.
Oh, you want to talk about methane on Mars?
Yeah, so
right.
I think I remember when that came out, and I remember wondering, I can't remember off the top of my head, you mentioned that was measured telescopically.
Yes.
So do you mean a ground-based telescope?
I do. There are in fact, let's see, how many? There are in fact 3 different independent measurements of methane on Mars that have been made, one from an orbiting spacecraft and others telescopically. The telescopic one is actually generally in the community most carefully done, but it is difficult, as I think you were pointing at, to do this from Earth, because you have to look through Earth's atmosphere and then successfully remove it in order to see the methane in Mars is farther away.
Are these results that you're putting an upper limit on the methane, are they casting doubt on those measurements, or are they generally interpreted as, those were sort of once in a century outgassing event that they just happen to catch?
For sure, they're casting doubt on the measurements. I think no one is willing, well, no, I won't say no one. It is a diverse science community. Few are pounding the ground and saying they were completely wrong. Most of us are sort of waiting to see. I mean, curiosity is still going. We make methane measurements. We check for it every 3 months or so. We have a regular cadence where we repeat 5 measurements in the space of 3 months, so we're monitoring it annually. If we get through 1 or 2 Mars years and we don't see it again, I think you're going to hear a lot of these calls for the detection. Was the detection real? There are already critics of the detection in various aspects of it. On the other hand, the best way to know is to send a spacecraft to orbit around Mars and look for methane, and to include an instrument that would look for not just methane, but other trace gases. So there are ways of knowing the answer to this question definitively, but I think the rover is going to provide great constraints.
Great, thank you so much.
Matt?
You showed positive and negative topologies on that map, and so I was wondering, without a sea on Mars, how do you set sea level? What is 0?
Right. What is 0 on Mars? I don't precisely know the answer to that question. I believe 0 was set. I do not know. I don't know how 0 was set. I was going to say that it's the average, but it's not the average because the volcanoes of Olympus Mons are considerably higher. They're like 25,000 meters, and the low point is in the 5,000 to 6,000 of meters. So I'm wondering if it's a global sort of area integrated average, but I don't know for sure. I'm going to go check now. Do you know the answer? You're a student of Mars, and you worked on this mission.
I think the sea level definition is the average height of the equator around Mars. I think that's how it's defined.
Aerially averaged.
Okay. Yes.
So funding aside, what ultimately do you think is going to limit the lifetime of the mission?
Funding aside was going to limit the lifetime of the mission. Well, yeah. I don't know, you in the audience, if they wanted to shut off the rover, would you object? I mean, I would kind of object. We spent all this money to get it there. I mean, once it's there and it's operating, we might as well keep operating it and driving and seeing what we're going to find. So hopefully,
but what's going to break first?
Hopefully, nothing will happen there. Well, so the rover is powered by a nuclear power source. It's a radioisotope decay, generating heat, then transformed to electricity. So unlikely that that's going to fail. That could last 15, 20 years. Which makes some of the engineers and scientists on the team like, oh my gosh, I'm going to be working on this 15 to 20 years. So it's probably going to be something mechanical. All of these parts are extensively tested. They're sort of warranted to 2 years, which is the length of a primary mission. Because it's the space program, they're tested to withstand 3 to 10 times that. But it's a harsh environment. The temperature fluctuations are huge, and that places a wear on the mechanical parts. So it will probably be some sort of actuator or some sort of connector between the power bus and the rover that interferes with its operation, or that interferes with its communication on Earth to Earth. Those would be the critical fatal things. I mean, 10 years later on, the Opportunity rover that landed in 2004 in January and was warranted, the primary mission was 90 days, still 10 years later is still going. It has 2 bum wheels and it has 2 broken science instruments, but it's still going and collecting great data, and there was a paper in Science 3 weeks ago based on its results.
So it seems like Curiosity is in road trip mode right now.
We're road tripping. We've kind of got the blinders on and drive.
So I was wondering, what percentage of a day is spent driving, and what kind of science, if any, are you going to be trying to do during the road trip?
Yeah, so good question. There are a few, maybe I'll go back, although I'm not sure it'll be apparent from this image. There are a few waypoints that are set up, and they're indicated by the triangles here on the map. And they don't have, some of them are just people's initials that have identified these points. Because we have this amazing orbital data, it's actually 25 centimeters per pixel, we're able to identify interesting geologic features that we might want to stop at. So as we drive, we're driving to these particular waypoints, scoping them out with our cameras, and if we're decided they're sufficiently interesting, then we're making the decision to stop. And so, so in terms of science, we're hoping to continue to follow the stratigraphy, basically from where we did the detailed analyses, and make sure we understand all the rock contact relationships heading all the way to Mount Sharp, continuing to do things like make methane measurements and atmospheric monitoring, but that's what we're doing with the rocks.
Thank you.
Mm-hmm.
How does having this sort of detailed data from now, I guess, 5 different points on the surface, since Sojourner, how do the different landing sites compare? How are the Spirit Opportunity sites different from Curiosity and then different from Phoenix?
Yeah.
And then, I sort of related to that, does it contribute anything that there's 2 different operational instruments on the surface? I mean,
you mean 2 different rovers?
yeah. I mean, I don't know if they're close enough or whatever, but do they experience similar weather conditions, because of planetary systems?
Exactly. Good question. Okay, so I'll answer the second question first, which is having 2 things better. So I think 2 things are better, certainly from a perspective of atmospheric monitoring, because yes, you get 2 different simultaneous samples of what the temperature is doing. The Curiosity rover actually has a wind speed indicator. You can get atmospheric opacity. So the more weather stations you have, the more you build up data about how the atmosphere changes, what the weather currents are like. Also, the benefit of having more rovers is that you get to explore more geologic locations. I mean, imagine if someone, if you, alien civilization, sent a spacecraft to Earth, and you landed in one location, and you were going to examine the rocks and determine the history of Earth. How would you do? You might determine the history of that location, but it's by building up data from multiple sites that we really have this detailed understanding of how our own planet developed. And that map I showed that had all those little dots with different minerals and stratigraphy. I mean, the lesson, I think, from the last decade of exploration is that Mars has an incredibly rich record, much like Earth, filled with water-rich environments from its early history. And it's there for us to explore from orbit and from the ground.
Thank you.
Oh, and actually the other part of your question was how the landing sites are different. Well, some of them have evidence for acidic environments. Some here have evidence for neutral to alkaline evaporative environments. The Spirit site has evidence in one location for a hydrothermal system fed by a small, fumarolic volcano. So it's different. I mean, like Earth, it's different depending where you land.
Thank you.
So studying Mars drives home that even for a planet within a potentially habitable zone, there may only be a window during its life history when life could possibly evolve. If you consider the results of the rovers plus Kepler, how far back does that whittle the likelihood of finding a planet that can support life?
The are we alone question. And how rare or not is a place like Earth? I think it's difficult to say. So we have sort of 3 good samples in our solar system of planets who are quasi-Earth-like: Venus, Earth, Mars. We see what happened to Venus, this sort of runaway greenhouse, and we see what happened to Mars, and Mars was a lot like Earth in some ways for its first billion years. In some ways, Mars is on the edge of habitability right now. I could give a different talk about present-day evidence for small amounts of water on Mars, but we're talking microbes. We're not talking about rich ecosystems sustained through time. And you mentioned the results from Kepler, the search for Earth-like planets. They're finding a lot of candidates. They're not necessarily finding them in the places, in the orbits that we expected. So I think it's too soon to say. I think it's causing a lot of head scratching and reassessment of results of how common planets like ours are, and the answer may be not very common.
My question's about education and communication. I mean, you asked the question before, would everybody in this audience care if you're funding a cut? And probably it's self-evident that the people who would come out here tonight to hear your talk would probably care a lot. I think a really kind of frightening thing that's going on, certainly in the US today, is an increasingly anti-science perspective. There's a lot of ignorant people in very high levels of government in this country. In fact, I would guess your funding could very much be in jeopardy. So I'm wondering, is there an arm to what you do that is communications and public relations? I mean, not everybody can wrap their head around the kind of things that you were talking about tonight, but I bet what you know from this is a big secret to a lot of people. So I'm just wondering, what do you do to spread the word and get more people interested?
So the question is, how do you reach the public, broadly speaking? Well, so I'll first speak of the various official efforts. So I'm here giving this public talk, and a number of individual scientists are doing the same. But we reach the number of people in this audience, and you're a self-selected bunch. NASA has actually several of its websites and social media won Webby Awards for having awesome websites with pictures and images. There's a rover Twitter feed that you can follow. There's also an alternative rover Twitter feed that is probably run by someone at JPL, but it's called Sarcastic Rover. It's actually really funny. So you should follow the real rover, and then you should follow Sarcastic Rover. And so there are these social media mechanisms as well. And the website at landing, that instantaneous moment, hundreds of millions of people logged in to check out the website. So there is this nascent, at least curiosity when we do something really awesome and cool that, oh, hey, yeah, I want to check it out. So there's something there. The question is, how do we tap that better? I think the answer, NASA has all these programs reaching out into K-12, folks speaking at colleges and universities. I think it really comes mostly through the schools. But there are other ways as well. Talk to your friends about at parties and see what they say. Do they support space exploration? If not, talk to them. Tell them why you're here and why you think this is cool. No easy answer.
We'll just take two more questions and then wrap things up.
Can we take 3 more since there are 3 people?
Okay, 3 more if you're going to insist.
Thank you again for sharing your. Oh, I'm sorry. Thank you again for sharing your experience with us. Mine's more of just sort of a day-to-day data keeping. How much of the data collected is resident on Discovery? All that they've ever collected? I'm assuming there's sort of a point you reach that you clear the slates and start collecting new. Once it's been successfully transmitted back to Earth.
Resident on Discovery, you mean stays on the rover?
Right.
Yeah, okay, so let's see. I'm probably going to get the numbers slightly wrong, but there's basically a few tens of well, actually it's a gigabit. So there's a few tens of gigabits, divide by 8 to get bytes of storage on board the rover. Typically the average transmitted per day. There's no interplanetary internet yet. Actually, this has been proposed. It's not a bad idea. It only costs 35 million-ish or so, but if you say the words interplanetary internet around Congress, you kind of get laughed out these days. Similar to your question. But it actually would not be that expensive to increase the data return from the present 500 megabits, so divide by 8. Okay, we're not getting very much data back per day, right? You can download this in like 10 seconds off a good Wi-Fi connection. So we are somewhat data limited in what we collect, but it all eventually gets sent back to Earth. Like all the science data collected gets sent back to Earth, and then it's deleted from the rover.
Okay. Thanks.
To keep the storage space.
Yeah, exactly. I was expecting once you're confirmed that it's been transmitted and received accurately, then you can get rid of that.
Then it gets deleted, and every day this is tracked. There's actually a data management person who every day reports on the data management status and exactly that, and then uploads the sequence of data deletes from data management.
So if I could ask just a brief follow-on, if it's so slow in being able to transmit what it's collected. Once, like if it stops collecting today, how many more days of transmission does it need to
clear out the
clear it out, right? To share everything it's collected.
Let's see.
Roughly.
Typically, we have enough in there that it would probably be about a week.
Okay.
Or so.
Thank you very much.
Sure.
Okay. Over to that side.
So my question is to do with the seasons. You mentioned there are 4 seasons on Mars. Like how different is the weather between 2 seasons?
Well, it depends where you are on the planet. So we're at the equator, and we're there for a reason. It's the warmest part, and the differences between seasons are less. So if you're at the polar regions of Mars, it is quite different. It gets so cold, for example, at the south pole of Mars, you build up this seasonal layer of CO2 ice, which happens at 145 Kelvin. So that's substantially below our balmy 273 Kelvin freezing point. But during the summer, that CO2 completely sublimes, and indeed water ice in some locations starts to sublime as well, and temperatures at the poles, they don't get above freezing, but they creep up to within tens of degrees of it.
Thank you.
And the last question.
Yeah, hi. Could you explain what the wind patterns are like on Mars?
I'm sorry, could I explain?
The wind patterns.
The wind patterns. Oh gosh.
Just like.
You're the atmospheric focused person here.
Okay, since you give me that opportunity.
You have a second talk that's loaded on my computer.
Absolutely.
No, not to be overly facetious, but so the wind patterns on Mars, actually like our Earth, this is kind of a theme. They're complicated, and so there are various winds that head from the poles. They're similar to like Hadley cell type circulation. There are latitudinal belts. As well. There are local winds in and out of Gale Crater that are actually quite interesting because of the location of, because of the existence of a big topographic boundary. You're more of a wind expert. Want to add anything to that?
The only other thing I'd emphasize there is that when you have about a quarter of the entire atmosphere condensing on the winter polar cap and then evaporating back into the atmosphere, moving over to the other pole and condensing there, you get tremendous north-south circulations of air in the atmosphere, which is something we have nothing really analogous to here on Earth.
So that's the big seasonal change, is this mass movement of vapor off the poles and deposition on the other pole.
Okay. Well, thank you everyone for coming this evening. I hope you've enjoyed things as much as I have.